Good morning. Thank you for attending an Introduction to Tolerance Rings webinar. I want to thank you for attending today. The purpose of the webinar is to give you the basics of the engineering and applications of the tolerance ring. We're going to have a 30-minute presentation followed by a question and answer period. For the question and answer period, it's easiest if you just put your question in the questions tab in the dashboard, and our presenter, George, will be able to see that and get to your questions as they come in. So I'd like to introduce George Speyes, our mechanical engineer for USA Tolerance Rings.
Hi, good morning, everyone. Again, my name is George Speyes. I'm with USA Tolerance Rings. I'm the senior mechanical engineer here. And today I'm going to be providing you with a quick, condensed version of what tolerance rings are all about, how they can be used, how to design for them. So I expect this presentation to be about, somewhere between 20 to 30 minutes long with times for question and answer at the end. And again, as Dan mentioned, any questions that you may have, just please enter them into the questions box provided through GoToWebinar. So without further ado, let me get started on the presentation. So our contents of discussion today, we're going to cover a little bit about what the company is, how tolerance rings work, their benefits, part identifications, and some of their applications. So a little bit about the company. We've been making tolerance rings in America here since 1961. All of our rings are produced at our facility here in wonderful New Jersey. We specialize in our custom solutions, specific engineering needs, and we cover a whole gamut of industrial applications out there, from consumer products to automotive to oil and gas and aerospace. We provide rapid turnaround prototyping of samples for all different projects. And we have ISO 9001 certification, and we're currently working on obtaining our IATF certification as well. So what exactly are tolerance rings? Well, they look like a letter C with a bunch of bumps on the outside. They look simple, but what they actually do and provide are very complicated. So a general definition of a tolerance ring is that it's a circular fastener used for joining or mounting cylindrical parts. They contain spring-like waves, corrugations, or bumps on their outside circumference and inside circumference, depending if it's an AN style or BN style. So an AN style ring has the bumps on the inside, and a BN style has the bumps on the outside. What are the parts of a tolerance ring? Well, we have what we call the strip thickness, and that's the actual thickness of the raw material that's fed into the machinery before the tolerance ring is corrugated and curled. Then we have the wave or corrugation height, and that actually includes the material thickness, and that is a nominal reference dimension. It's a reference dimension. It's something that we use as a gauging method for when we produce the part. We have the total ring width, which is the axial width of the ring. Then we have what we call the effective or wave width, which is actually the approximate width of the bump or corrugation itself, and that's determined by what tool we happen to use. And here we have an isometric view of a tolerance ring, and I'll talk about some of the key parts of it, its anatomy. So we have the gap, which is the space between the ends when it's installed in between components. There's the shoulder, which is basically each end of the wave or bump, and that's the strongest part of the tolerance ring. That's what gives you your retention and holding force. We have the pitch, and that is the distance from valley to valley or peak to peak of the waves. It's the wave spacing on the circumference. Then we have the flat or the planish, and that's the flat part on either side of the shoulder of the tolerance ring. Typical applications of tolerance rings are for mounting of ball bearings. They can be used to transmit torque. They can fasten, join, and center components. They allow for thermal expansion and contraction between components of different materials, those that have different coefficients of thermal expansion. They can handle radial loads. They can allow for reduction of machining costs by relaxing tolerances in certain instances. So in some applications that would typically require a ground finish, you can actually go to a machine finish when using a tolerance ring. They're a good alternate for when a pure press fit is undesirable, and they permit the joining of ideal dissimilar materials in different parts of an assembly. They can allow for slip torque applications to prevent overload damage, acting almost like a torque circuit breaker, where slippage won't occur until it goes above a certain amount of torque hold, and then when the torque hold goes below that point, the tolerance ring will again engage and act to transmit torque. They can be used as a manufacturing aid to center or hold parts. And for elastic applications, they can typically handle radial tolerances between about 15 10,000ths of an inch for small rings and up to 15 thousandths of an inch for larger rings. Typical functions, fastening and joining, such as a knob mount, transferring a torque, such as an impeller on a shaft, and for mounting ball bearings. Sometimes the tolerance rings application overlaps a few of these different categories. Some typical fastening and joining applications are with knobs and handles. And the image on the right shows an application with dissimilar materials where the customer did not want to use adhesives, so they chose a tolerance ring instead to allow for future removal of their components. They've been used around brush motors. The outside polymer or plastic of a brush motor assembly can be rather fragile, and it can tend to fracture or crack if too much forces are applied to them, such as using a set screw or other securing device. So brush holders are a good application for securing tolerance rings within the motor housing. You don't have to use epoxy. You can just put a tolerance ring around it and push it into place. Tolerance rings come in many different sizes. Just to give you a comparison, this ring's about, maybe 10 or 11 inches in diameter. This is actually used to hold a huge wheel hub in place during assembly prior to putting on the lug nuts. They can be used for mounting stators within electric motors. They can be used for mounting resolvers and encoders. So for electric motor application, the tolerance ring will prevent the stator from rotating by providing a torque hold between the OD of the stator laminate stack and the inside of the housing. So when you have an aluminum housing that's expanding and contracting at a greater rate than the stator mounts, the tolerance ring will hold that retention force throughout the thermal range. Sometimes those stator laminates can be rather fragile or brittle. So by applying a tolerance ring, the smooth side against it, it can reduce particle generation. Typically with a motor mount, a band style ring is used. That's where we have the bumps on the outside. That way the bumps dig into the housing and not into the stator laminate stack. Some applications do call for an AN style for a motor mount, but that's really up to the customer's preference. Tolerance rings can be used for transferring torque. In this application, we have a flywheel mounted onto a dryer tumbler. I have a little animation here to show you. And that was actually an AN style ring shown in this animation with the bumps on the inside. They can be used to mount pulleys, and they can transmit high torque depending on the strength and diameter of the mating components. I mentioned they can be used to prevent against torque overload by allowing the components to slip relative to one another above a certain torque load. Now, torque slip applications are a little bit tricky because it won't necessarily slip at a specific torque point, but there's a bandwidth range in which a tolerance ring can be designed for certain applications to actually slip. But torque slip applications require quite a bit of experimentation on the customer's behalf to get the right torque hold. High radial loads can be handled when you put the tolerance ring in a groove. I'll discuss this more later on. This is referred to as a centered arrangement. It can be used for transmitting torque in gears. Usually it's plastic gears that the tolerance rings are used to transmit torque, because the torque transmittal required of steel gears is usually much, much greater than what a tolerance ring can handle. So most application involves gears. It's more for polymer gears that aren't enduring very high torque loads. And mounting ball bearings is probably about 60 to 70% of the application of tolerance rings. That's historically where they were first used back in the late 1940s, early 1950s to compensate for thermal expansion and contraction. But since then, they have been used for many other different types of applications. You can mount a ball bearing with it in a steel stamped housing, in zinc die cast housings, in aluminum housings, and in plastic and polymer housings. For motor rotor assemblies, when you have a bearing pair on each side, the tolerance ring will actually allow the bearing to float to compensate for axial thermal expansion of the shaft. I'll talk more about that a little bit later in the presentation. Tolerance rings can be used for mounting bearings in tubes. In this application, the customer wanted to use a ball bearing in a standard stock steel tube, but they had to weld the tubes together, and that caused distortions in the steel. So they no longer had a true centered inside diameter due to the welding and heat distortions that were created. So by using a tolerance ring, it compensated for the out of roundness, and they did not have to go back and do a secondary machining operation. This is one of my favorite charts because it really gives the nuts and bolts of why tolerance ring is so great for thermal applications, where you have one component expanding or contracting at a greater rate than the other component throughout a thermal temperature range. So with the tolerance ring, or excuse me, let me start out without a tolerance ring. If you were to press in, say, a 2-inch OD ball bearing, the pressing force at room temperature would be about 500 pounds or so. That's an interference fit of a ball bearing in a housing. But as that housing heats up, let's say it's an aluminum housing with a steel ball bearing, you lose your retention force on that tolerance ring. So when you hit about, maybe 170 degrees Fahrenheit, that outer race is now going to slip. It's going to creep, or the ball bearing itself can fall right out of the bearing pocket. But with a tolerance ring, the same room temperature press fit on that 2-inch OD ball bearing might only be about 320, 350 pounds or so. But throughout the temperature range, because each of the bumps on the tolerance ring acts as a spring, it's holding the ball bearing in place. So it's not going to fall out throughout the thermal range. So again, this graph really shows a significant way of how tolerance rings work with thermal growth. So with a typical pure pressure application of a 2-inch OD ball bearing, it'd be a 10/10,000 traditional interference fit. But with the tolerance ring, you can relax those tolerances, going to say maybe plus or minus 1,000 of an inch on the ID, and it'll still hold up ball bearing throughout the thermal range, much greater than a pure press fit would. So ball bearings can compensate for thermal expansion. They provide constant retention under high RPMs. They allow for increasing component tolerances, going from ground finishes to machine finishes. And they can eliminate the need for adhesives, O-ring, rubber boots, retainer plates, and set screws. We usually recommend a minimum wall thickness of about 2 millimeters for steel. And by wall thickness, I'm referring to when you have a housing mount. So the wall thickness would be this width right here. That is your wall thickness. So if you're using a tolerance ring in a steel housing, we recommend this distance from here to here to be at least 2 millimeters. And these are minimum requirements. Going thicker is always beneficial. If it's an aluminum housing, we recommend a minimum of 3 millimeter wall thickness. And if it's a plastic housing, we recommend a minimum of 4 millimeter wall thickness. This is because the tolerance ring is exerting radial forces back and forth between the outer race of the ball bearing and the housing ID pocket. In some cases, you don't have to do a second machining operations with as molded parts, you might be able to just use a tolerance ring in place as long as that draft angle is kept to a 1/2 degree or less and the bearing pocket is not too deep. You can allow for some degree of angular and radial misalignment. This is a zinc die-cast housing, and if you have airflow through your product, like if you have a way to actually cool the bearing, because the tolerance can have waves on the inside, it'll actually allow for better heat dissipation by giving a little bit of a clearances between the valleys of the tolerance ring to allow for airflow. But you would already have to have designed some sort of way for air to flow past the ball bearing based on your application for the heat to be dissipated in those applications. Tolerance rings can be used with preload washers. I'm sure you're familiar with the brand Smalley. Sometimes the preload washer or wavy washer is redundant. Sometimes it's not needed. Sometimes it is. Sometimes they're using conjunction. So it really depends on the application whether or not a preload washer is still desired when using with the tolerance ring. Most of our customers stick with the wavy washer just because they're used to it, but it really depends on the particular application whether it's needed or not. Because in some situations, the tolerance ring itself acts as a preload device, except for at points where the temperature changes direction. So on the right, we have a typical bearing pair set on a shaft. We'll assume an aluminum housing on the left-hand side and a steel end bell on the right. We'll assume that the inner race of the ball bearing is press fit onto the shaft at both ends. So when it heats up, the steel shaft will expand, actually expand lengthwise, so that bearing needs to float a little bit in that tolerance ring. So when the temperature rises, the aluminum inside diameter will expand while the axial steel shaft is expanding. Thus, it allows the tolerance ring to actually float prior to damaging the bearing. Because if you put too much axial forces on a bearing, especially when it's static, not rotating, you can Bernal the race surfaces. You put little bumps in it from the balls actually pressing into the inner race. And that's a big no-no. You don't want to do that because you'll have premature ball bearing failures. And as the components cool, the shaft will contract. It'll reduce its length in the axial direction, pulling the ball bearing back into its initial room temperature condition. And when it cools, the aluminum housing would contract, and thus the spring force on the tolerance ring is increasing once it goes back to room temperature. So that's how tolerance ring can allow for a little bit of axial float in a lot of instances. They act as almost as their own preload device based on their initial press and force. Tolerance rings can compensate for bearing misalignments. So in a press fit, if you have two housing ends and your bearing pocket holes are not lined up properly, the axes are not collinear, you can get some out of roundness in the spinning. You get excessive forces being generated on your bearings and your shaft, which all amount to premature failure of the ball bearings. And again, the misalignment here is exaggerated for observational clarity for the presentation. The tolerance ring tends to be somewhat more forgiving than a pure press fit. So with the tolerance rings, yes, you still have some misalignment, but it's not as severe as it was before. Because what happens, one side will be much more compressed than the other side, than the other wave, and vice versa. On the other side, this wave is less compressed than this wave. So it allows the shaft to better find some sort of centering. It helps the shaft to self-center itself. So when this occurs, the stresses are less severe on the shaft and ball bearing when you have bearing pockets that are not in proper alignment. So yes, you still have some misalignment, but it's not as severe as it would be with a pure press fit. because the tolerance rings tend to allow the shaft to find its natural center. Noise, vibration, harmonics. That's a real tricky subject to get into. I won't get into all the Fourier series and various different third order, fourth order differential equations on this. What we recommend is that you really just have to test different tolerance rings to deal with noise and vibration issues. Within a vibrational system, the tolerance ring acts as a spring, though. Remember that. It's not a damper. It won't absorb energy. It won't dampen it. It acts as a spring where it will absorb the energy, then release it. A pure damper will absorb and dissipate the energy, but the tolerance ring will absorb the energy, then release the energy. So that being said, how can a tolerance ring be beneficial for reducing noise and vibration? Well, in some cases it is, in some cases it is not. It depends on the harmonics of the system, the natural frequency of the bearings, and everything comes into play there. The best way to deal with noise and vibration with a tolerance ring is just to test a few different samples, see which ones gives you the least amount of noise and vibration. So if the natural frequency of your system falls right about here, and your bearing harmonics are here, you've got an overlap of the bearing harmonics with the natural frequency of the system, which will give you a little bit of noise because you get wave addition going on where they overlap. So if you put a tolerance ring in place, and it's just the bearing harmonics over here to A, which is farther away than the natural frequency of the system, you'll get less noise and vibration. Hey, that's what you want. If you put a tolerance ring in place and it shifts this bearing harmonics all the way over here to B, again, you move it farther away from the natural frequency of the system. So you'll get less noise and vibration. But in some cases, if the bearing harmonics are moved to C with the use of a tolerance ring, you'll get more noise and vibration because now you're with wave addition, you're adding this bearing harmonic wave onto the natural frequency of the system wave to get even more noise and vibration. So the objective when using a tolerance ring is trying to shift the bearing harmonics to either A or B. And again, that's done through trial and experimentation. So I mentioned that an AN style tolerance ring has the bumps or waves facing inward. They're designed to be installed by slightly compressing the sides. There's typically a gap between the ends of an AN style ring and the free state. Now, when would you use an AN style ring? Well, anytime the OD of the inner component is fixed and the ID of the outer component can be modified, that's when you would go to an AN style ring. And I say typically because there are always a few exceptions. So an AN style ring would be used around the outside diameter of a ball bearing. You put an AN style ring in a housing bearing pocket, then press the ball bearing into the AN style ring. BN style have the waves facing outward. They're on the outside circumference. And they're installed by slipping the BN style ring axially over a shaft. And they tend to be self-retaining when released. So to install them, you would just slightly expand them, slide them axially onto the shaft, and the BN style rings will typically have an overlap of their ends, or the ends will touch in the free state. Where would you use a BN style ring? Well, it would be for situations where the housing ID is fixed, but the shaft OD can be modified. So when the outer component ID is fixed and the inner component OD can be modified, that's usually where you go to a BN style ring. Or where there's concern where the waves could scratch softer material, such as with the motor mount that we showed earlier on. We do not want the waves to embed into the stator laminate stack. We wanted them to go into the aluminum housing. With the designing for the tolerance ring, you can go with what we call a free, a piloted, or centered arrangement. And that just refers to how the tolerance ring is actually retained. With the free arrangement, you'd have to use like an outside plate of some sort, which would act as a stop for when you press, say, the shaft into the tolerance ring. A pilot arrangement gives you one edge to work with that acts to actually retain the tolerance ring. And a center arrangement is essentially a groove, either in the housing ID or on the shaft OD. to actually retain the tolerance ring. Depending on the design, either 3 of these scenarios can be used. Now, naturally, the centered arrangement with the groove is the most expensive to manufacture, but it provides the best margin of safety in the design. The free arrangement is less costly to manufacture, but it provides the least amount of margin of safety in the design. So it's really a judgment based on the particular application, which is better to use. And these are just some specifications for how wide to make your groove. Typically, you want to make that groove about 1 millimeter wider than the nominal axial width of the tolerance ring itself. So just add 1 millimeter onto the width of the tolerance ring, and that'll give you what the normal recommended groove width is. So I talked about a center arrangement, and that's where you have a groove on the components. And I find this to be terrific for handling radial loads because it allows the radial loads to be spread out among the components. So when a radial force is applied, the waves of the tolerance ring are compressed slightly on one side, but the radial forces are shared by the tolerance ring and contact between the inner and outer component. This allows you to exceed the actual radial capacity of the tolerance ring by going with the center arrangement. And these are just some nitty-gritty of some of the engineering formulas for how a tolerance ring works. Little k is the spring rate of a single wave or bump, and this is the formula for little k. And that way you can determine the amount of force, in theory, that each individual wave would exert. That determines your actual retention force per wave. And that can, based on the number of waves, that gives you your total axial retention force per a given tolerance ring. Big K is the spring rate encountered when one cylindrical component is pressed relative to the other within the elastic range of the tolerance ring. Big K is typically calculated by n, the number of waves, times little k, divided by 5. So essentially what this is saying is that 20% of the waves are doing the work of reacting to any component's movement relative to the other. And that these formulas, they were derived based on the Strybeck bearing equations, for those of you who are familiar with those. So it falls in line very much with the calculations done for balls within a ball bearing. So the tolerance ring is elastic within a certain range. It has elasticity within a certain range of wave compression. Then as you start to go in the inelastic range, it starts to yield and the radial capacity will drop off. Inversely, the torque capacity, how much torque a tolerance ring can take, is based on how much the waves are compressed. So when you compress the waves, the torque will continue to increase. In an ideal design, you want to find some sort of a common ground between radial capacity and torque capacity. How are they installed? Well, for A-style rings, you just squeeze them radially, push them into the bearing pocket. B-style ring, you would slip the BN ring actually onto the shaft, having it pop into a groove or in a piloted arrangement. And then you would need to use most applications you need to use a press, such as a pneumatic hydraulic or arbor press. And the installation force is encountered usually about 1.5 times the retention force. In other words, it's easier to pull the components apart with that has a tolerance installed between them than it is to initially install them. And that's just because of the snow plowing effect. When you're pulling them apart, the waves have already been compressed. When you're installing them, you're acting almost like a snow plow to push the wave downward as the components are pushed together. So again, an arbor press or pneumatic press are good for most applications. Some applications you can actually do it by hand as long as the axial forces are less than, say, 80 pounds or so. But that's usually for smaller diameter tolerance rings, like maybe 15 millimeter range or less in diameter. Now, our part number nomenclature actually tells us what is going on with the ring. So the first column is tells you if it's AN or BN, whether the waves or bumps are on the outside or the inside. AN, BN, that's column 1 style of the ring. Column 2 is the diameter of the ring. If it's a metric ring, which is signified by the X here, this would be 5 millimeters. For this English unit ring, it's 1.25 inches. Column 3, that just indicates whether it's a metric or standard or English unit designation. If there's an X there, you know it's a metric designation. If there's no X there, you know it's a English unit designation. Column 4 is the axial width of the ring. So this ring right here would be 6 millimeters axial width. This ring here is 3/4 of an inch axial width, 0.75. Fifth column is a type of material. C stands for carbon, S stainless steel. The sixth one just indicates it's a non-standard ring. So whenever you see a number past the last letter, that just means it's a non-standard configuration. You'd have to actually refer to the drawing to figure out what is non-standard about it. And we can make the tolerance ring out of several different materials. 301 stainless steel is our most commonly used material. It can handle temperatures up to 450 degrees Fahrenheit. 301 stainless steel tends to be very corrosion resistant and resilient to a lot of different chemicals out there. Some of our inventory are carbon steel. Carbon steel cannot handle the temperature ranges up as high, and it tends to be susceptible to corrosion and oxidation. But for same given diameter, a carbon ring can be slightly stronger, but there's more post-processing involved with it, a little bit more complicated to provide. We'll make them out of exotic alloys, such as Hastelloy C276 when the customer asks for it, and also Monel K500 for customer-specific requirements. And we'll make them out of 316 and 316L stainless steel as well, which is a softer form of stainless steel. Just a general pitch comparison, the distance between the waves. So on the towards the left-hand side, we have what we call a smaller pitch, which is actually more bumps on the outside compared to a larger pitch, which is 9.4 millimeters here, which shows how the spacing is much greater. So this is just a comparison chart to give you an eyeball visualization of what the distance between peak to peak or valley to valley would look like for different pitches of tolerance rings that can be used. Sometimes we'll deviate from standard pattern groups. Now, why do we want to deviate? Well, if we change certain parameters, given the same nominal ring diameter, we can increase the amount of torque hold, the radial capacity, and get higher axial insulation removal forces. So if we increase the material thickness, that'll give us that higher torque, higher radial capacity, and higher axial insulation removal forces. If we decrease the pitch, that is, we add more waves to the circumference, we can get higher torque, higher radial capacity, and higher axial insulation removal forces. If we increase the pitch, putting a greater distance between the waves, we get a slightly greater elastic limit. If we go with a higher wave height, we tend to get a slightly greater elastic limit. Now, all these parameters can be changed within certain limitations because we have to compensate for what the machinery can do, what the tooling can do, and what the material itself can do. So we're limited to how far we can increase or decrease material thickness, how far we can increase or decrease pitch, and how far we can change the wave height. So in summary, tolerances are great, simple, proven, cost-effective solutions. They can allow for easier and quicker assembly, may reduce the number of components needed. They can reduce machining costs, allow for standardization of parts, allow for different thermal expansion, for instance, joining of ideal dissimilar materials in different parts of the assembly. They can handle radial loads, transmit torque, and they can be used for slip torque applications to prevent overload in certain applications. They can be found in automotive, oil and gas, conveyors and automation, consumer products, and many other industry classifications. So to get started on the project, the best thing to do would be to submit through the new project information form. It's a link on our website to start a project, and it asks for all those pertinent questions that we need to know. So it asks the correct questions of you so that you can provide a response, and from your response, we can provide a tolerance ring recommendation. The form asks for specifics such as the diameter of the components, the tolerances on the components, what can be changed, so on and so forth. We'll provide samples for prototyping whenever we can. If we don't have anything in stock, we may have to make some. Tool set fees may apply, but that depends on the specific application. We always try and provide samples out of stock, but sometimes we don't have anything in stock available that would be suitable for the particular design constraints provided. If you go to our website, there's plenty of literature there, more information. The website goes more into depth than this presentation did, and our website is listed below. And I'd like to thank you all for being an attentive audience. So at this point in time, I'm going to pass it over to Dan, and just submit your questions if you have any through the questions box. Thank you all very much, and have a wonderful rest of your day.
Again, I want to thank everyone for attending today. If there are any questions, in the lower right, there's a question box. You can submit them and we'll try to answer them as best we can. If you think of one later, please email us or visit our website, usatolerancerings.com. All right, doesn't look like we have any questions today. I hope you enjoyed yourself, and everyone have a safe and wonderful week. Thank you. We do have one question, ceramic materials. But our attendee has left. Here we go.